that'll give you a countdown timer.
Okay.
That's when your talk ends and you run into your question time. And everyone who wants to have lunch will start to yell at you.
Okay, got it. I'll try not to hold up lunch. Well, hello everybody. My name's Jared Mills. I'm from the University of Arizona. I study direct imaging instrumentation, both ground and space. So unfortunately, I think this talk is going to be a little heavily emphasize that more than some of the other techniques, but I'll try to do all the other ones justice. What I'm here to talk about today, which one works? Are these extremely large telescopes that we are currently building. So this is the GMT, the Giant Magellan Telescope, the ELT, the European Extremely Large Telescope, and the 30-meter telescope, the TMT. This is not going to advance because it's a PDF. Sorry? I can just page down, right? Okay, I'll do it that way. So these are the extremely large telescopes. One thing to know about how we talk about these, that we use ELT both to describe this class of telescope. It also now refers to what used to be called the European Extremely Large Telescope. So I'm just going to use ELT to refer to that one in addition to the broader class of telescopes. And so to sort of set the table here, just consider the telescopes we have today. These are ones that we can use right now. There's the 5-meter, 6.5-meter telescopes, the 8 meters, so now this is Gemini, the VLT, Subaru, and the LBT. Both the VLT and LBT are actually multiple 8-meter dishes. And then there's the 10 meters like Keck, the Canary Islands 10-meter SALT and Hobby Everly. And then I've highlighted here the 22-meter LBT, which works in Fizeau mode like a filled aperture, more or less like a filled aperture 22-meter telescope. And of course, there's the interferometers like Keck, VLTI, and Chara that can get very high angular resolutions, but these are not filled aperture telescopes and are a little more difficult to use in terms of getting an image and aren't quite as competitive in terms of sensitivity. Like I said at the beginning, there's some caveats here. So because of who pays me, I'm a GMT partisan. And I work on direct imaging instrumentation. So apologies to the TMT and ELT. I hope that I'm not giving them short shrift here. And RV transits and all the other possibilities for studying exoplanets with these telescopes, I'll try to do justice as we go. So starting out with, this is the Giant Magellan Telescope. This is one thing that I wanted to point out here is there's vehicles. There's a semi-truck under there, to sort of give you the idea of how gigantic these telescopes are going to be. These are some of the biggest scientific instruments, maybe the biggest scientific instruments that humans have ever made. So this is going to the Las Campanas Observatory, which is down here in the Atacama Desert of Chile. This is very dry, very interesting place to go. Zooming in on that, so the way all these telescopes are segmented. So you can't just make a 25-meter piece of glass very easily anyway. So the way the GMT works is it's 7 of these 8.4-meter mirrors. These are basically the same mirrors that are on the LBT, just being polished and configured to be a single optical surface. So this is one parabolic surface. And here I've called out that the diameter from edge to edge is 25.4 meters. Because of the fill factor, it actually has the resolution of a 24.5-meter telescope. Those aren't typos, and you'll get confused because sometimes you'll see it referred to as a 24-meter telescope, sometimes a 25-meter telescope. There's a good reason for that. By collecting area, this actually works out to like a 21.6-meter telescope. So that's just accounting for the fill factor. Like I said, this is at Las Campanas. It has an elevation of just over 8,000 feet, and we're aiming for first flights in 2025. There may be several lies told during my talk. The most flagrant ones are going to be the first flight estimates that I give here. All of these numbers are pending funding. They're all subject to schedule slippage due to all the many things that can happen when you try to build an instrument like this. And the GMT is a consortium of many different organizations. Several US universities, Australia, Brazil, and Korea are all involved in addition to these US universities. So I'm going from south to north here, not in order of diameter. So this is the European Extremely Large Telescope. It's up here just, it's basically near Paranal at what's called Cerro Amazonas. So this is making use of smaller segments. So these are, I don't know how well you can see that. Maybe you can see it better over there. These are hexagonal segments that are about 1.4 meters apart. It's a whole lot of them to make a 39-meter telescope. First flight here is also scheduled for 2025. And I should say that both the first flight numbers for the GMT and the ELT are both not necessarily the entire primary mirror. So there's plans to start out with a subsection and make sure things are working. And this is a project of the European Southern Observatory. And last but not least is the 30-meter telescope, the TMT. The name says it all. And it is currently destined for Mauna Kea Observatory on the Big Island. Again, this is hexagonal segments, 1.4 meters across. This is definitely the highest one. It's almost at 14,000 feet. And the target for first flight for the TMT is 2027. This is an artist rendition. It is not intended to be in orbit, so ignore the stars behind it. That would be an awesome LUVOIR. So this also is an international consortium. So there's a number of US universities, including the one the campus we're standing on right now, plus India, China, Japan, Canada. So these ELTs are extremely large. And I showed you that semi-truck before. And I'm about to show you a comparison, and this is not to sort of say, look how small these other telescopes are, because they have their own issues with size and how do you get them where they need to go. But I just want to sort of communicate like some of the other telescopes that have been talked about and what I think astrobiologists think about using in the near term. This is the Hubble Space Telescope and the James Webb Space Telescope to scale on the ELTs. They fit in the central obscuration hole of the telescopes. So the hole in the center of the GMT is as big as the Hubble Space Telescope primary mirror, and the ELT its hole is bigger than the James Webb. So that's just communicating how gigantic these astronomical instruments are. So the obvious question is why? And bigger is always better, so maybe it sort of seems obvious, but there's a few things to understand about these. So what I'm showing here is what is known as the CCD equation, the signal-to-noise ratio of a photon noise-limited or Poisson noise-limited observation. So what I have here is the flux from the star. So that is, just think of that for now as photons per meter squared per second, multiplied by the area of the telescope and multiplied by the exposure time. So what you have here is the total number of photons collected over the square root of the number of photons collected. That's the noise. So it's proportional to the area, which means that the signal to noise is proportional to the diameter of the telescope times the square root of the exposure time. So this is for an unresolved or seeing limited source. So the key point here is I haven't put in anything about the photometric aperture. This is the aperture size of the telescope, but I'm not talking about the circle that you actually put down in the image to add up the photons. This is just using sometimes we refer to this as the light bucket mode. We're just pointing one of these telescopes at a star and collecting photons. So this is the signal to noise equation that describes that. And you can just follow the math and work out that the time to reach any given signal to noise is proportional to the diameter squared. So right away, that's a pretty good reason to make a giant telescope. You make it twice as big, your time goes down by a factor of 4. But there's something else to consider here, and this is when you're at the diffraction limit. So I avoided putting in Fourier transforms into the talk, but we have to sort of bounce off that idea. So what this is what we call the Airy disk, or the Airy pattern. So this is what the point spread function, the image of a star through one of these telescopes, looks like if it's diffraction limited, not limited by atmospheric seeing. And I'll explain a little more about atmospheric seeing in a little bit. And so this plot is just a line out through this image of a star showing you how that flux is distributed. And a key thing to know about this is the full width at half max of this Airy pattern, and this is essentially a Gaussian, just for reference, is approximately equal to the wavelength of the observation over the diameter of the telescope. Bigger telescope, that gets smaller, which means that you have better resolution. So this, effectively, the image of a star gets smaller, which means you can see more stars next to each other. So we call this the diffraction limit. So now if you were able to use one of these telescopes at the diffraction limit as if it was in space, for the sake of argument, this is what the signal to noise would look like in a background limited case. So now what I've done is, instead of the noise being just the photons you collected, the noise is the background noise times the area of the PSF. And the reason for that is, now because we're in this diffraction limit, what I'm talking about is just adding up the photons in this disk. And so I have this size of that disk, which the width is lambda over d, so the area must be lambda over d squared. So now this is the signal to noise ratio in this diffraction limited, background limited case. If you follow that through, now the signal to noise ratio is proportional to the diameter squared, and the time, what you might call the sensitivity, the time to reach any given signal to noise goes as d to the 4th power. So you double the size of your telescope. It doesn't go up by 4, it goes up by 16 times how much faster you can achieve any given signal to noise ratio. So this is a really powerful incentive to build these giant telescopes. This is why we're doing it. So how do we take advantage of this diameter? Well, to start with, we're going to build instruments. So spectrographs, which we'll use for radial velocity detection of exoplanets. They also do transit atmospheric characterization of exoplanets. We're going to have imagers. So this is, when I say imager here, I just mean exactly what you think it is. It's a detector that you point at a star with an exoplanet and add up the flux coming from the exoplanet. And then also coronagraphs, which I'm calling out from both of these because the coronagraph is what you would put in front of one of these to actually do really high contrast detection and characterization of extrasolar planets. So as an example of an instrument that we're going to use on one of these telescopes, this is from the GMT, and this is the GMT Consortium Large Earth Finder, or G-CLEF. And this has a wavelength range of it's basically visible, 350 to 900 nanometers, and very high spectral resolutions from 19,000 all the way up to 108,000. And this is, perhaps you would consider this the first light science instrument for the GMT. This is an ongoing project that is expected to be delivered when the GMT is ready to send light down it. One of its key science cases here is precision radial velocity. So this is to be able to detect very low mass extrasolar planets around nearby stars. So to do that, it's a vacuum enclosed gravity invariant instrument. It's fiber fed, so it sits on the floor of the dome. And so it doesn't rotate, it never flexes. It should be extremely stable. And to highlight this diameter advantage, one of their science cases is to look at a TESS M dwarf where a planet has been identified by TESS transiting one of these M dwarfs, and they're going to use this to measure the mass of that planet. And so on a 10 meter, like Keck, in 1 hour, you would achieve 1 meter per second at the photon noise limit. For the GMT, that goes down to 10 minutes. And the reason this is only d squared is because this is not assuming adaptive optics. This is a seeing limited observation where they're just putting a fiber and using this as a light bucket. The really exciting thing about this instrument is they think they can maintain an instrument noise floor of 10 centimeters per second. And so in 20 minutes on a 9th magnitude star, they would get 10 centimeters per second photon noise. That would limit their precision. I guess that's a typo that I didn't catch there. And I'll refer you to the GMT science book where I have a URL at the end of the talk for the exact details of these calculations. And so this is what comes out of this improvement in sensitivity that G-CLEF gets you. And with apologies because I just showed up today. Have you guys seen this plot before? Probably like 100 times this week, right? So just to remind you, this is orbital period of the planet. This is spectral type of the star. So there's Earth, right? So that's 1 year, and that's a G2 star. Down here, the TRAPPIST planets, there's Proxima b, And here's sort of our best RV precision right here. So if G-CLEF achieves its goal of 10 centimeters or better centimeters per second precision, they'll be able to detect planets around at 1 AU in sun-like star HAB zones. And so that's a really exciting thing, that this combination of the super stable spectrograph, the massive aperture of the Giant Magellan Telescope, and its photon noise limited precision gets us, is we'll finally be able to measure the mass and detect, discover, and measure the mass of an Earth-like planet with a ground-based radial velocity spectrograph. The TMT and the ELT have similar instruments planned, though not at first light. The TMT has started its second generation instrument, I guess you would say, down select process. And so they're considering a visible and a near IR high resolution spectrographs, again, at sort of the R of 100,000. And the ELT has high res, also a second gen instrument. It's done a phase A study, and it will do basically the same kind of science that G-CLEF does, out to R of 100,000. So like I said, that was a seeing limited instrument, or at least the science case that I showed you was a seeing limited application of that instrument. So to get from that d squared to that d to the 4th scaling, we have a problem when we're on the ground. That is the Earth's atmosphere. So another way to say this is stars twinkle. We all know the song. So the impact of atmospheric turbulence here is that stars are twinkling because as the atmosphere blows over a telescope or between you and the star, that the atmosphere is blowing temperature variations, or the wind is blowing temperature variations in the atmosphere between you and the star, causing index of refraction variations. This causes the light to be corrupted because the light is actually moving at different speeds as it goes through the atmosphere. And this also causes amplitude effects, not just the phase effects. And so this is a really nasty problem. And the best sites routinely deliver something like half an arcsecond seeing. So remember, I showed you that full width had half max of that Airy pattern. That was the lambda over d. What I'm saying is that at the best sites, that would be half an arcsecond across. Whereas with the GMT, we could go all the way down to 0.004 arcseconds if we didn't have atmospheric seeing. So we're a factor of 100 different if we just accept atmospheric turbulence between us and the stars. And so a key fact is that if you're seeing limited, the spatial resolution of any large telescope, anything bigger than about 10 centimeters, even a backyard telescope, will have this spatial resolution set by this number, half an arcsecond. And if you're using a backyard telescope, you're probably in a backyard in a city, and this is probably more like 2 arcseconds. But the key thing is making that telescope bigger won't improve your spatial resolution, and therefore won't get you anything better than d to the squared scaling. So the key thing we have to do to realize this full promise of these giant apertures is have adaptive optics, which is how we fix atmospheric turbulence. So the way an AO system works is we have our science camera. This could be that's not the warning I was expecting.
Running over on your